Hello and welcome to the following lesson on the standing waves required practical for the waves topic in AQA A-Level Physics. So in today's lesson we're going to be looking at that standing waves required practical and looking at deducing an experimental plan for this experiment. Now if you've been successful and learnt in today's lesson, you should be able to detail the relationship between a force on a string and the frequency of the string, carry out a required practical to investigate in this, and detail the properties of different harmonic oscillations. So in today's lesson we're going to look at the following part of the AQA A-Level Physics specification: 3.3.1.3, the principle of superposition of waves and the formation of stationary waves. In particular, required practical 1, an investigation into the variation of the frequency of stationary waves on a string with length, tension and mass per unit length of the string. So in your investigation today, your aim as a scientist is to derive a relationship between the frequency of a stationary wave with its tension, the length of the string with the frequency of the stationary wave, and the mass per unit length of the string with the frequency of the stationary wave. So if you can work out how the tension, the length and the mass per unit length of the string affect the resonant frequency, by the end of this practical you will have learned. So the materials you will need for this required practical are a signal generator, a vibration generator, a stand, a mass, a 1.5 meter length of string, a pulley which can be clamped to the bench, a wooden bridge which is slightly higher than the pulley, 100-gram masses on a holder, a meter ruler and an electronic top pan balance. So you would set up the apparatus as shown in the diagram. So you can see here what we've done is we have produced a standing wave on a string by using a vibration generator connected to a signal generator, a stretched string, a movable bridge and a pulley which is clamped to the bench, along with masses hanging off the end of the string. Now with this equipment you can investigate how you can change the mass per unit length, the length of the string and the tension of a string can change the resonant frequency at which the standing wave is produced. So what you would do is you'd adjust the position of the bridge so that the length of the string L is measured as 1 meter with a meter ruler. Now you can then increase the frequency of the signal generator from 0 until the string resonates at its first harmonic frequency, which is indicated in the diagram as there's a node at each end and a central antinode, which denotes what the first harmonic wave looks like. You would then read the frequency F on the signal generator dial. You would then repeat the procedure with the length of the string being 0.9 meters, 0.8 meters, 0.7 meters, 0.6 meters and 0.5 meters. You would then obtain a second set of results by repeating the experiment and then finding the mean value of frequency for each value of the length of the string. At that point you would then plot a graph of the mean of 1 over the frequency against the length of the string. You would then draw a straight line of best fit through the points and then find the gradient. Now the graph should be giving you a straight line through the origin, and the gradient of this straight line through the origin is 1 over FL. Now we know that the speed of travelling waves on a string is f lambda, where f is the frequency and lambda is the wavelength. Now when the string is vibrating in its fundamental mode, in its first harmonic, we can therefore say that the wavelength is equal to twice the length of the string. So therefore we can say V is equal to frequency times by 2L. L being the length of the string. Now we know that the gradient is 1 over FL, so therefore V, the velocity of the string, is given by the equation 2 over the gradient, and there you get your velocity in meters per second. Another way in which you can work out the speed of the stationary wave along the string is by the equation V is equal to the square root of T over mu, where T is the tension in the string in newtons and mu is the mass per unit length of the string in kilograms per meter. Now with a 100-gram mass hanging from the string, T would equal 0.981 newtons. Therefore mu can be found by weighing the 1.5 meter length of string on an electronic balance, convert that into kilograms and then dividing it by the length, which will be 1.5. Those values can be substituted into the previous equation to find a value for V, which can then be compared to the value obtained from the graph. Now the experiment can be repeated with different masses hanging from the string and different thicknesses of string to investigate the effect of changing the tension and changing the mass per unit length. Now just to clarify a few things, you can measure the mass by using an electronic balance, and therefore you can deduce the mass per unit length, or mu, by measuring the mass of the string into the length of the string and then dividing one by the other. So mu would equal the mass of the string divided by the length of the string. Now in addition to that, you can deduce the tension in the string is under by multiplying the mass hung off the string in kilograms by the strength of gravity. So we would say that T is therefore equal to mg. Now you can investigate how each factor affects the frequency of the first harmonic on the string. Now to do this, the other factors would then need to be kept constant if a factor is varied. So to alter the length of the wire, you would then, or string, you would move the movable bridge from the vibration generator. So you would move it backwards and forwards like that. To alter the tension on the string, you would then add masses to the string at the end, and then you can work out what tension the string is under. Whilst to alter the mass per unit length, you would use a range of different string samples to get different masses per unit length. So use different types of string or strings of different thickness. Now it's also important to note that doubling the frequency of the first harmonic whilst keeping the length, the tension and the mass per unit length constant will cause the string to resonate in its second harmonic, which is also known as the first overtone, with notes at either end of the central node and two antinodes. Now tripling the frequency gives the third harmonic, and so on. So what have we learned in today's lesson? We understand what stationary waves are. We know that nodes and antinodes are formed on strings where F is equal to 1 over 2 L times by the square root of T over mu for the first harmonic. That a formation of stationary waves are from two waves with the same frequency travelling in opposite directions. That stationary waves formed on a string and those produced with microwaves and sound waves can be considered, and then stationary waves on strings can be described in terms of harmonics. So if we've been successful and we've learnt in today's lesson, we should be able to detail the relationship between the force on a string and the frequency, carry out the required practical for investigation into this, and finally detail the properties of different harmonic oscillations. So thank you very much for watching this particular lesson on the standing wave required practical, which is part of the waves topic in AQA A-Level Physics. Thank you very much for watching and have a lovely day.